Yep. Okay, so your homework 1 is graded. If you haven't picked up your homework 1, they are right here. You can come pick them up. And if you have submitted them by paper, you have submitted a hard copy, you can pick up your paper. If not, then your graded homework should be essentially you can find your graded homework where you submitted it on Blackboard, right? With all the comments and everything, whatever you want to get. Your homeworks are graded by my grader. One of your friends actually brought up an issue with a grading, which I think he's right. So I need to talk to the grader if he did the same analysis to grade all of your papers. I essentially add 2 points to everyone. So yeah, please make sure to go over your graded homeworks and talk to me about any issues you may see. Okay. Homework 2 is also posted on Blackboard. I think from this point on, it is better for us to do the electronic copy. It will be less of a hassle for everyone involved. If you all agree to that, we can just remove the hard copy, save a little bit of environment. And yeah, so just submit them online whenever you're ready. The homework 2, I think has 5 problems, 20% each problem. Some of the problems are easier, some of the problems are harder. I just wanted to distribute the points evenly to make sure that to help you guys a little bit. But I'm pretty sure you can get a good grade out of homework 2 as well. Is there any questions about homeworks in general? That's the idea. So that's you essentially what you need to do if you want to submit electronically is that you don't need to type it in. You solve it on paper, take pictures of your paper, create a PDF file, and then submit on Black. The PDF file creation is a very important step. Yeah, you don't want to submit a couple of images to me or you don't have your grader's email. So you don't want to submit a couple of images to me. Any other questions? For graduates, yes. Yes. Not, you won't get the exact same question on the exam, but they will be similar, right? So you have to make sure you understand the solution, not just copy them, right? And these things actually, from my experience of teaching this course and dealing with your guys' exam, especially when dealing with circulation, people who copy the answer from somewhere get a 0 on their exam for that problem, like that circulation problem. So because it is all integration, you have to understand what the circulation is, how to deal with the circulation problem. It can become a little confusing because our mathematics is not our strongest forte in this department, unfortunately. So yeah, you have to make sure you understand the solutions, but the questions will be similar to, you may get some multiple choice questions, like 20 multiple choice questions, which are going to be worth 20% of your total grade, but those won't be a part of homework, of course. Other than that, everything will be part of homework. And what else? Okay. Your graduate students, today is the deadline for proposal submission. Most of you have already submitted your proposal. If you haven't submitted your proposal yet, please make sure to do so before the end of the class. And yeah. Pardon me? Not before 12, before the end of the class. Yeah, so that actually one of your classmates asked a very good question from me, send me an email and asked a very good question from me about the deadlines. On the course syllabus, on the course schedule, it says assignment due before a time, right? That means due before the start of the class at that day, okay? And we can do end of the class instead of a start of a class, but I'm assuming you are in the class and you cannot work on your homeworks or whatever in the class, right? So make sure to submit whatever you want to submit before the start of the class. Any other questions? Okay, so today we are going to finish chapter 2 and start chapter 3. The last part of chapter 2 we are going to cover is going to be computational fluid dynamics, or CFD. And this is just a very, very introductory, a very like simple introduction to CFD. We'll just talk about what is CFD, why do we use the numerical methods in general, and instead of an analytical solution or experimental designs. And then we will see some mathematics. In this homework, the homework 2, you don't have any CFD problems. But on your next homework, you will get a CFD problem. And what I'm going to do, I think we talked about your proficiency in MATLAB in previous lectures. There are some people who don't know how to use MATLAB or Python for that matter. What I'm going to do is to do an introduction to Python, actually, which is a more common programming language in data science nowadays. I'm going to post something on Monday for you guys to go over. We will cover the mathematics behind whatever you need today in the upcoming lectures as well. At the end of chapter 3 and chapter 4, we will have some CFD as well. And then you will get a question in your homework. Okay? Is there any questions or concerns or requests when it comes to programming or programming languages? Or no? Okay, that's good. Yes.
So the ANSYS tutorial is coming up this coming Monday.
Right? Yeah, that is for graduate students. Yeah, I mean, everyone is welcome to watch, but that is for graduate. So the ANSYS tutorial, graduate students, most graduate students, to bring everyone in the loop here, most graduate students are going to do a numerical analysis when it comes to their project, right? A CFD analysis. And they are going to use ANSYS Fluent. So what I'm going to do a tutorial on how to do a sample like aerodynamics project in ANSYS Fluent. I will also do OpenFOAM if I had enough time, which is an open source free software, Linux based. This is something that I use personally for my own research. And whoever wanted to do OpenFOAM, yeah, welcome to do so. Okay. Any other questions? So let's just start with the CFD, or computational fluid dynamics. So computational, CFD is an abbreviation for computational fluid dynamics, which I'm pretty sure you could have guessed. And essentially, it's a lot of methods that are used to simulate fluid mechanics or fluid dynamics or fluid flows in general using computers, right? All of these methods together are called computational fluid dynamics. So we are going to have very different hosts of methodologies that are used under the umbrella, that are named under the umbrella of CFD. But the first question you want to answer when it comes to numerical methods in general is why? Why do we want to use computers to simulate a fluid flow or to do a stress analysis, to do anything engineering related? Why are computers better if they are better, right? This is the first question you want to answer when it comes to numerical methods. And this is something I want you to try to answer. Why do you think we have to employ numerical methods? Or we have to create the methods first, then like simulate them. So we are essentially adding complexity to our problems. We already have the governing equations, right? If we could just find analytical solutions for those governing equations, we wouldn't need to come up with these new methods, right? The new schemes. Why do we use computational fluid dynamics? What's the problem with the governing equations we have? Let's focus on fluid mechanics parts of it. You want to jump in? It looks like you want to jump in.
Too many unknowns and not enough equations.
So too many unknowns and not enough equations. That's one. Too many unknowns. So more than equations. That's your point. Okay. That's one guess. Anyone else? Complex computations, I guess, right? Paul, right? Paul here brought up an interesting issue here, actually. Everything in real world is three-dimensional, right? But in order to find analytical solutions for those small problems that we can find analytical solutions, we always make a lot of assumptions. Most of the assumptions are removing one of the dimensions, right? Like airflow analysis, it's a two-dimensional analysis. And it's true for like a host of problems that we can solve analytically by finding equations for it. So yeah, that's computations are very complex, are going to become, in real world computations are very complex. What else? Not, this is unbelievable. Okay. What else? You can compare different things. So it is going to give you more freedom, I guess, right? More freedom in analysis, right? Is that your point? If it's not, we can, I guess that. Yeah, I guess that's the correct way of looking at it, right? So essentially, you will be able to analyze different situations easier compared to an analytical solution. What else? Yes. So the solutions you are getting are for 1 point. Is that what you said? But if you have a distribution, if you have like, let's say p equals to x squared plus y squared plus z squared, that will give you the pressure at any point, right? That is the ideal way, the analytical solution. That's the goal, huh? Okay, that makes sense. Okay, easier. I don't know. It is easier. Let's call it just easier for. So to find the pressure contours, instead of putting like all the numbers and calculating a pressure, you can just use a computer. Okay, that makes sense. What else? Okay, I guess we already have enough ideas. So let's go over them one by one. Too many unknowns. The problem here with these too many unknowns here, if you have too many unknowns, you won't be able to solve it using a numerical methods as well, because numerical methods are going to be based on the equations you already have. So this is not true. You should have as many unknowns as equations, but in general, in fluid mechanics, that's a huge problem. Fluid mechanics and aerodynamics. Usually, the governing equations usually are one less than the number of unknowns we have. So we usually have to come up with another equation that relates the governing equation together. But that is true for analytical and numerical methods, right? So that is not specific to analytical methods. And all of these together, let's combine them together and talk about this. So the governing equations we are dealing with, the most general form of the governing equations are partial differential equations, right? To be able to find an analytical solution for a partial differential equations, we either have to simplify it, right? Make a lot of assumptions, or the other option is there is no option. There is no way to solve those governing equations. The governing equations we have here in aerodynamics or fluid mechanics in general are coupled to each other. So it is essentially, in the most general form of things, it is essentially impossible to come up with an analytical solution. If we could get an analytical solution, we would have, because it would have made our lives much easier. Like then we could have feed that analytical solution to a computer and get the pressure contours and whatever we wanted to get. So that would have made everything more easier and also more accurate. That's the biggest point here. Everything would have been more accurate. But since it is impossible to solve the most general form of analytical solution, most general form of governing equation, we have to come up with a new method. A new method here is going to be your CFD, or numerical methods. There are three different mathematical methodologies that we have here that we can employ to be able to solve an aerodynamic problem, right? There are many methods, actually. I'm going to name three main ones. Finite difference methodology, finite volume, and finite element. Who in this class has passed the finite element course we offer? Dr. Deng, right? So you have seen, what did you do in your finite elements course? So you essentially transformed your partial differential equations in a computer feedable form, right? That was the idea, to be able to feed your partial differential equation to complete. And that's what we do with all of these methods. These two are a little more complex, finite volume and finite element, and we definitely cannot cover them in just one lecture. But finite difference is the easiest one. That is very popular I guess it was very popular in the earliest stages of CFD development, like in the 70s and 60s, because it was the only method. It works based on linearizing your governing equations. Governing equation. What does this mean? What is the main source, or what is it in our governing equations that signifies the nonlinearity of the governing equations, if you will? What do you think? Like, from a mathematical standpoint, our governing equations are nonlinear, right? What do you see there that is telling you that the equations is not nonlinear? Or let me tell you the answer, because I think it's a very complex. I could have asked it in a better way. The partial derivatives, partial x, partial y, partial, whatever, right? Small changes. The idea was, if you recall from your numerical methods course and from your mathematics, this signifies a change, right? Can be signifying a change in pressure in the x direction, right? It can be signifying a change in velocity or whatever, right? If the change is linear, what does a linear change mean? It means like if you draw p versus x, it is changing like this. So p is equals to ax plus b, right? It has a linear function, okay? If the change is linear, then we can transform this partial derivative to just a difference, delta p over delta x. That's the idea. So with the finite difference method, we are going to linearize the governing equations. But how should we do it in a way that doesn't decrease or doesn't compromise the accuracy of the simulation, the accuracy of your solution? Because the system is a nonlinear system. We cannot just randomly make it a linear system. So let's think of this airfoil here. Let's say we want to find the flow field or the velocity distribution around this airfoil. What we do in the finite difference method is that the first thing you do is you assign a control volume. Then you divide this control volume to small sections. These are not parts of the volume. Okay. And then, like let's do at each point. These points are the locations of interest. We are going to assume, and this is the assumption we are making when it comes to numerical simulation, that the changes in like velocity for this specific problem between these two points are linear. So partial, if you are moving in the x direction, partial u partial x is going to be delta u equals to delta u delta x. Okay. How does this help us? Essentially, it's going to make our lives very easy. If you have the velocity at this location, which is for this specific case is going to be your flight velocity, right? This is going to be your velocity at all of these points. This grid, this is called the grid. This grid is something you have defined. So you know the delta x here, right? You will be able to find the velocity at these points. Then you apply the same analysis to these points, these points, these points, these points. You have the velocity field. Okay? It is usually a little more complex than this, but this is the idea, the general idea. But how should we do this transformation? How should we transform a partial derivative to a difference? It should be through a mathematical operation. It cannot just be a random assignment, right? What do you guys think? What should we do here? Just think about a mathematical operation that transforms partial derivatives to a difference.
Does it have anything to do with the Laplace transform? Or am I thinking the wrong direction?
It doesn't have anything to do with the Laplace transform, but you are getting close. Okay, you are getting warmer. I don't think you guys can guess this, but this is we are going to use the Taylor series. Does anybody remember what the Taylor series was? Have you heard the name Taylor series? Okay. So what was the Taylor series? Taylor series could give us the value of a function f at one point using the value of that function at another point. That was the idea. Okay. So f of I, this is the value of function at point I, let's call it point 1, right, is equals to f at point 2 plus, what was the rest of it? Does anybody remember? You have seen this before, right? Okay. F prime over x, exactly, multiply and x factorial, but that's multiplied by, I'm sorry, that's multiplied by over 1 factorial, 2 factorial, right? Plus f double prime, this is 1 factorial, 2 factorial, x squared, this is delta x. So the difference, the distance between the two. We are looking at f versus x. This is 0.1, this is 0.2. And this is delta x. And then so on and so forth. F triple prime, delta x3. Okay, so this was the general form of your Taylor series. But let's apply it to our problem here, our problem of interest. Let's look at this point. I'm just going to take a couple of these points here and bring them here. Okay, let's call this point I and j. I plus 1 and j. I plus 1, j plus 1. I, j plus 1. I minus 1, j plus 1. I minus 1, j. We can also do the 7 else, right? So this is going to be our central point. Then I plus 1 is going to be the next point in the x direction, next point in the y direction, and so on and so forth. Is this clear? Okay, it's just a naming scheme. We could have said 0 and 0, 1 and 0, 1 and 1 and 1. It's just a naming scheme. And let's apply this idea here to the velocity of these points. So velocity at point I and j, and we are moving in this direction. We want to find this point. We want to find the velocity at this point using the velocity of this point. Let's say we already have the velocity of that point. It's going to be u I plus 1 and j plus partial u partial x, which is your f prime divided by 1 factorial multiplied by delta x plus partial squared u partial x squared delta x squared over 2 plus the rest of it. Is this clear? Are we following? Are we all following? Okay. So Taylor series, we haven't done anything that relates to numerical simulation yet. It's just the application of Taylor series to our grid, to our mesh, right? Let's move this to the other side. So let ui and j minus ui plus 1 and j. And let's divide everything by a delta x. Is going to be equal to partial u partial x plus partial u squared, partial x squared, delta x over 2 plus the rest of it. Yes. No. No. You have to apply. That's a little more complicated. We can talk about it. Let me finish this, and if I see there is interest in class, we'll talk about it. If not, then we can talk about it after class. Okay. So if we ignore these parts of the Taylor series, what do we have here? We have partial u partial x is equals to delta u divided by delta x. So we have linearized the partial derivative here. That's the first order partial derivative, though. For the second orders, it's a little. We have to apply the same methodology, but it's going to be a little different. And this part is going to be called the error truncation error, for that matter. Okay. And using the point that is in front of your original point of interest is called the forward difference methodology. So, forward difference method plus an error. So what does this tell you? We are able to linearize the governing equations, but it always comes with an error. How to deal with this error itself is a separate course, right? The error propagation and all of those problems are very, very salient in numerical methods, CFD in general, are very important, very important. Okay, so what if we use this point instead of the point that is ahead of our point of interest? What if we use this point? You could have gotten to the same solution. There would have been a small difference it would have been partial u, partial x plus your error. Or we can actually move the error to the other side. That doesn't really matter. This methodology using the point behind your point to linearize the governing equation is called the backward difference. So we have used the forward difference here to linearize the partial derivative or backward difference. Since in all of these methods, you are going to see a second derivative of x, this is actually, you are using the first derivative. This is called a first order accurate. You don't need to, it's just, you just should know the name. That's I plus 1 j. Is there any question so far? No. Okay. We can also combine these two. This is going to be a little more interesting. We can combine the backward difference and forward difference by just adding them up. get to another linearization scheme, which is going to be giving you the partial derivative of u with respect to x at point I using the point ahead of it and the point behind it divided by delta x squared, or 2 delta x squared. So this is called the central difference, and this is second order accurate. And here you have a bonus point. Use the Taylor series to find this. The central difference linearization for the partial derivative of u with respect to x at points I and j. That's I and j. And this is second order accurate. If you do the analysis, you will see that this term will go away. So the error is going to start from your third power. That's why it's called the second order accurate. Okay, so are we following? Oh, it's a very, this is going to, are we following? Not so-so? Right. So-so. So where's the question? What is the question? Yes.
I just have like an observation. It just looks like it's delta U or delta X.
That's it. That's the idea. The only reason we did the whole Taylor series thing, it was to understand the error, right? There is an error, right? Just have to deal with that error. It is not equivalent to an analytical solution. That's the point. Yes.
Does making the grid smaller reduce the error?
That's a very good observation, actually. So if you make the grid smaller and smaller and smaller, you're essentially reducing the error, right? In a very simple system, though. In some systems, in some more complex systems, your simulation will become unstable with very small errors, with very small grid sizes, especially in the simulations that involve marching in time, right? In those type of simulations, there's a number called the CFL number, or the current number, that sets a limit for your time step size versus the grid size, right? Because if the time is involved, you have to linearize the time derivatives as well, right? And that means that you are marching, and you are not marching continuously in time anymore. You have a time step. You have the solutions at time 0, then time 0.1, 0.2, 0.3, 0.4, right? So that's thank you for that question. Okay. Anyone else? So how should we apply this, though? Like, we understand the error, we understand the Taylor series. How should we apply this, or where does it apply? Let me actually see. Who asked about the second derivative? There was one person who asked about the second derivative. Yeah, you asked about the second derivatives, yeah? Yes? Okay. So I'm going to do this. I'm going to give you another bonus point. This is actually going to be 2 bonuses because you cannot find this in the book. So 2 bonuses. This time it has a W. Right? And you find linearize partial squared u to partial x squared for me. Okay. Just to give you a hint here, when you apply the Taylor series to this, your f1 is essentially your partial derivative at I and j, your first derivative. is going to be your first derivative at like point ahead or a point behind plus the rest of it. So you write the Taylor series for the partial derivative. Then you replace whatever you have with these values here, right? It's a bonus point, so you don't need to understand this at all. But it will help you a great deal if you, in understanding what is going on here, if you do the bonus point. Okay, so let's move on. We only have the first derivative. How can we use this? Your book has an example. That's actually the best way to understand this is to write a code and solve the problem, which is the thing you are going to see on Monday. I'm going to post a lecture on Monday. You don't have to watch it. I guess you have to watch it because it will be a part of your homework. If there's anyone who can't, because it's Monday is a wellness day, right? And we cannot have any lecture. If there's anyone in class who cannot watch the lecture on Monday, it's not gonna be a live lecture, so I'm just gonna post it and on Friday probably or Saturday. If there's anyone who cannot watch that lecture, please let me know. You can come to my office. We'll go over the whole thing together, right? Because I don't want you, or let me put this, I cannot force you to watch a lecture. I'm going to record it. Yeah, it's going to be recorded. It will be available to you on Saturday, hopefully, if I can. So it will be available on Blackboard. I will probably post it on YouTube. This is what I did for previous years. And then I will send the link on Blackboard. Okay. So I'm not going to go over the example problem in the book. I'm just going to write it down. So the problem in the book has actually solved the conservation of mass equation using these methods. As you can see, we all have first derivatives here. So based on the methods we have already learned, we should be able to linearize this problem. How do we do that? You first linearize the time derivative. This derivative is going to be three derivatives, like partial u, partial x, partial whatever, plus partial v, partial y, partial w, partial z. You have to linearize all those three. And you will be able to feed that equation to a computer, which you're going to see how to do that in a video lecture that I'm going to post. This is something we did in class for my heat transfer class. I asked the students to write the whole thing in Excel, and that would be easier to visualize. So probably this is what I'm going to do for the Monday lecture as well, so you can see the effects of whatever you're doing, like real time. And it's going to be better than just writing the code, right? Okay, so this is the CFD, a very small introduction to CFD we want to have today. And we are going to do some more numerical modelings as we go forward in chapter 3 and 4, but those are not going to use like conventional CFD methods. Those will be a little older CFD methods, like panel theory and all of those things that was developed in like 60s and 70s to deal with aerodynamics, to solve aerodynamics problem. Is there any questions so far? Is this confusing at all? Yes. You have one yes. Which one? This is a I wanted to give you an example of a governing equation that you can linearize, or in CFD term is called discretize. No, it is a partial differential form, right? You have to linearize it, right? Or discretize it. This is the terminology CFD people use. Discretize the governing equation. But we can always talk if you have further questions. The reason I include this part in your lecture, essentially in our lecture, is because I don't think it makes any sense for a mechanical or an aerospace engineer to graduate without any knowledge of CFD. So I think it is crucial in this day and age, right, to understand numerical model, the basics of numerical model. Okay, so let's solve some example problems. Some of these are from your book. Some of these are like examples from your book. Some of these are book problems. And then we'll be done for today, and we'll be done with chapter 2. The first example we want to solve is to calculate the circulation. We are given a velocity field. This is the velocity field. U is going to be equal to y divided by x squared divided by y squared. And v is going to be equal to negative x divided by x squared plus y squared. And we are asked to find the circulation around a circular path of radius 5 meters. And the units of circulation, I'm going to see the units. Okay. What was the equation we had for circulation? Anyone? Line integral of VDS, right? Which we could have used the theories we learned about to turn it to a double integral. What did we have here? Del cross V ds. This is element of area. Just have to make sure not to confuse these parts. This is element, this is path on the line. So the first one is a small element of path here, and the second one is a small element of area. Okay. What should we do? I'm going to give you a couple of minutes to think about this. And see how we can approach this problem and solve the problem. It's that we want to calculate circulation around the circle, right? Whenever you see a circle, that is your geometry, whatever, you want to convert whatever you have, transfer whatever you have to circular or a spherical coordinate system, because that will make your life easier, right? You don't have to, but that will make everything easier. Okay. So we essentially want to transfer these two. These are in Cartesian coordinates. We have y's and x's, right? We want to transfer these to a cylindrical or spherical. In 2-dimensional, they are the same coordinate systems. Okay. How can we do that? What was x in cylindrical coordinate system? What was y? And what was x squared plus y squared? R cosine theta. What about y? R sine theta. And what about x squared plus y squared? R squared. Okay. So we have all this. I think it should be very easy to transfer the coordinate systems for u and v. Let's do that. So if you do that, what are you going to get? R sine theta divided by r squared. So you're going to get sine of theta divided by r. Here, r cosine theta divided by r squared. You're going to get negative cosine of theta divided by r. But this is u and v. We are still in the Cartesian coordinate system. We want to find vr and v theta. Vr is the velocity in the r direction. V theta is the velocity in this direction, right? But u and x, u and v are the velocities in these two directions. Let me change the color. Right? Is this clear? Vr is in radial direction. V theta is in tangential direction to the circular path. Is this clear? Okay. So we have u and v in cylindrical coordinate system, but to be able to use them, we have to find vr and v theta. Okay. So what is the angle these make with each other? This is your angle theta, actually. You have angle theta here. You have angle theta here. So your VR is going to be u cosine of theta plus the projection of u, and this is going to be u cosine of theta, right? And the projection of v, again on VR, is going to be v on VR is going to be v sine of theta. Okay, is this clear? So we have two vectors. We are just projecting here. We have u and v. Okay, u and v, right? Let's forget about v theta for a second. We want to find the projection of u and v on VR. Projection of u on VR is going to be u cosine of the angle between the two, right? Projection of v is going to be v cosine of the angle between the two, which is pi over 2 minus theta, right? Which means that it's going to be cosine of pi over 2 minus theta is equals to sine of theta, right? So it's going to be v sine of theta, right? So VR is going to be u cosine of theta plus v sine of theta. We can do the same analysis for v theta. So your v theta is going to be u sine of theta plus v cosine of theta. That's actually negative u sine of theta because of the direction. Okay, is this clear? If you understand up to these points, the rest of it is just the integration, right? Hopefully you understand those points. Yes.
Can you remind me again what U and V represent?
U is the velocity in the x direction in Cartesian coordinate system. V is the velocity in y direction in Cartesian coordinate system. And W is the velocity in z direction in Cartesian coordinate system. But we don't have W here. So essentially, a velocity vector in Cartesian coordinate system is ui vj plus w car K. Velocity in cylindrical coordinate system is VR, ER. That's the unit vector. Unit vectors are cylindrical coordinate system, V theta, E theta, and VZ, EZ. Okay, so we were able to convert Y and X to R and theta, but we had to transfer U and V to the cylindrical coordinate system as well. Okay. So what is the next step? Just plug in the values of U and V. If you plug in the value of U here, you're going to get sine theta, cosine theta divided by R, right? And here you're going to get negative cosine theta, sine theta divided by R. Okay? What does it mean for R, for VR? We're going to get positive sine theta, cosine theta divided by R minus sine theta, cosine theta divided by R. What will be the VR? Be more confident. Should be 0, right? So U sine theta, cosine theta divided by R plus V minus cosine theta R divided by R sine theta. Same thing, so your VR is going to be 0, which means that there is no velocity in this direction, right? In these directions. We are going to only have velocity in tangential to this circular direction. Plug the values in. We are going to get 2 sine theta cosine theta divided by R, right? Because the signs are the same, are going to be the same. You're going to get 2. That's actually no. Let me write this here. So V theta, for U, we had sine theta divided by R. So negative sine theta divided by R multiplied by sine theta plus negative cosine theta divided by R multiplied by cosine theta. Okay. This is going to be equals to cosine sine squared cosine squared. So minus 1 over R sine squared plus cosine squared theta. What is the value of this? Does anyone remember from mathematics? 1, exactly. So your V theta is going to be negative 1 over R. Yeah. So we have transformed the coordinate system successfully after a very lengthy process. Again, you didn't have to make this transformation, but you have it. But it is going to make everything easier. So V in the Cartesian coordinate system is going to be 0 ER plus 1 over R E theta, which means that we are going to get negative 1 over R E theta. We have the velocity vector. Okay. What is ds? No, this ds here. Not this one. This one. That's it. This is actually a small element on the surface, right? It is a small this ds, which your book, I don't know why your book uses the same. value for them. This is d small s, this is d capital S. So this ds is the small element on a surface. This is a small element of the surface area. Okay, just make sure not to confuse those. Okay, what is this ds? Itself, ds itself is a vector. Okay. To better understand this, let's find this delta S. Every S, which is S1, S2. In the cylindrical coordinate system, every point can be represented as with a radius and an angle. So we're going to have R, ER, plus theta, E theta. R1. Does this make sense? Like in Cartesian coordinate system, each point could have been xi, y, yj, zk, right? In cylindrical coordinate system, it's going to be R1, a radius, right? R2 or whatever. Does this make sense? Yes? Yeah, we have some confused people. But you have to let me know where is the confusion. Okay. And then for the second point, we can write R2 ER theta 2 E theta. Your delta S, this delta S is going to be equals to delta R, which is R2 minus R1, ER plus delta theta E theta. Let's make this a smaller and smaller and smaller. Your ds is going to be dr ER plus d theta E theta. Okay. Do we all follow this? Yes. If you have a couple of yeses, other people didn't respond. Come on. Which hopefully means that you are either sleeping or following. Both of them are fine. Okay, so we have the S, we have the V. Let's go back to the original formula. VDS. V, the inner product, dot product ds. So we're gonna get 0 VR. I'm not gonna write, let's actually write it. 0 ER plus negative 1 over R E theta dot product dr ER d theta E theta. Dot product of two vectors. Recall was just the components multiplied by their normal unit vector in that specific direction. Okay, so we're gonna get the dot product of these two vectors is going to be 0 multiplied by dr ER plus negative 1 over R d theta E theta. This is 0. So inside that line integral, we are not going to have any dependence. Inside that curve integral, we are not going to have any dependence on R anymore. So your circulation is going to be equal to negative curve integral of 1 over R d theta. Oh, there was one thing that I missed here. This theta, this S here, is represent, this is the arc length, this arc length, right? This arc length is going to be r, this r multiplied by this theta, right? We are looking at this arc length. So this has to be r theta, r theta. And for ds, we're going to get r d theta, e d e. So essentially, we are going to get another r here, and you're going to get the positive integral of d theta from 0 to 2 pi, a whole circle, 2 pi. So your circulation is going to be equal to 2 pi. 2 pi meters squared per second. Okay. Any questions? Is this confusing at all? Did we all follow? I just want to make sure we all followed, because this is yes.
I get all the steps separately. Like, why do we need all these intermediate steps? We use that circulation problem down that negative 1 per hour.
So if we didn't have the ds, then this would have been ds. How would you take the integral? This integral. You don't know the dependence on r of r on s, right? Pardon me? You had to find ds in terms of whatever like functionality it has, right? It is the s is a function of r and theta here. So you have to make sure to break down the path to its smallest components, if that makes any sense.
Could you explain again why that thing that you missed, the r ended up canceling out the 1 over r, because you missed like an r somewhere?
Yeah. That's the look. Yeah, sure. That's the location of. That's actually s. If you can have a dimensional analysis, right? S's dimension is meters, right? So to be dimensionally consistent, dimensions of r, er, and e theta, whatever that are inside those unit vectors, have to be in meters as well, right? So from a dimensional perspective, you have to have r and r theta, because theta's dimension is degrees, radians, okay? But that's just a dimensional analysis. Let's say this is your two circles in a cylindrical. This is your S1. This is your S2, right? I intentionally gave you a case with different R's and different thetas. Or we could have actually done that here. Doesn't really matter. We want to find delta S, which is S1 minus S2, right? We want to find the distance between these. So this distance has two components. One is the R component, which is R, right, ER. The other part, the distance, the component of distance, is going to be how much you have moved on this arc, right? And how would you characterize that? With the arc length, which is your angle multiplied by the radius.
The original angle multiplied by the radius?
The difference between the angle. Yeah. So like here, the R's are the same. So we are dealing with dr, so we don't put it to 0. But theta, the distance between these 2 points, is going to be this arc length, right? So it is r theta 1 minus r theta 2, or rd theta. Okay? Is it clear now?
Yes.
Okay, we wanted to solve more example problems, but I guess we are not going to have enough time. Whenever I solve an example, I try to solve the most complex example to make sure that we cover every part of a problem. So if you think you're confused, I don't want to say that was the goal, but I predicted your confusion. I always predict your confusion. Don't be scared. Your exams are going to be easier, and I don't want to say are going to be easier. But if you understand this, you won't have any problem solving the exam problem. And if you are confused, please reach out to me and ask your questions. Is there any questions? So there are 2 more problems that we wanted to solve, but I guess we are running out of time, and we can just I don't want to. We can just continue we can continue discussion on Wednesday. I try to be as quick. The other 2 problems are easier, so hopefully we don't have to stay on them this long. One of them is in the book. Yeah, one of it is example 2.9. Okay, so that's it for today. Have a great weekend. Let me end the stream here.